All right, question 14. You got a wire that's 100 centimeters long. Okay, so starting from 0 to 100. Now what we're going to do is we're going to cut it. Don't know exactly where, but we're going to make that x, which makes this automatically 100 minus x. Now what we're going to do is we're going to split this up between a square and a rectangle that's got some restrictions there on its shape. So let's call this the rectangle. We'll put x units on the rectangle. We'll put 100 minus x to the square. Now we're told that the rectangle is such that the width here and the length are related because the length is 5 times the width. Okay? And let's over here a square. Well, the sides are the same for a square, so that's easy. So this x here is going to be on the perimeter of the rectangle. That's 5 w's here, 5 w's here, ww. That's a total of 12 w's. So the width of the rectangle here is going to be x over 12. Okay. For the square, it's fairly straightforward. The perimeter for the square, I've got it as the 100 minus x, and that's going to be 4 e's. So 100 minus x over 4 is equal to e. So the sum of the areas here, okay, well, the w here is x over 12, but let's go back to this. The area of that rectangle is going to be 5w squared. The area of the square is going to be e squared. But now I can make a substitution, okay, plugging in the expressions that I just evaluated a few seconds ago. And I can now I have this in terms of x. And I might even expand this out a little bit further because I know that the derivative of a constant goes to 0. And the derivatives of polynomials are pretty easy to work with. So here's my expression for the area. That's what I'm going to take the derivative of. So area is going to equal, area prime I should say, is going to equal 5x over 72 minus 25 over 2 plus x over 8. I set this equal to 0. And I'm going to put those two x terms together and take out the x. So it'll be 5 over 72 plus 1/8. Minus 25 over 2. If I bring the 25 over 2 over, okay, notice that those can be added together, and then if you find the common denominator, which would be 72 in this case here, this will end up being 14 over 72. And when I bring that up here and multiply it through here, I'm going to get that x is equal to actually, I'm going to write it out as a decimal here. 64.3. Whoops, I'm sorry, you can't even see that. 64.3. Now, I'm going to do it like this here because this is what I want to check. This doesn't tell me, though, whether this is a minimum or not. Okay? For how much of this wire here that I commit to the rectangle, I could commit either 0 to it, all 100 of it, or just some x to it. Okay? So x is the rectangle here. If I put it at 0, if I make the amount that I dedicate to the rectangle equal to 0 and plug that into my expression here, so if I make x equal to 0, I get that the area is 625. On the other hand, if I push everything up and make x equal to 100 so that there's no square, I just use the whole thing to make the rectangle here, this makes the area equal to 347.2. Now I've gone through and done those calculations. All that is plugging 0 into this to begin with and then 100 in for x in this expression here. However, if you plug in the 64.3, you get that the area is 223.2. So it turns out this right here is where the minimum occurs. It's the smallest area here, and that occurs when we put 64.3 centimeters here on the rectangle. Okay, so in this case right here, what I'm doing here to determine that I've got a minimum is there is a restriction on the domain of this function that x can only be between 0 and 100. I found only one critical number here at 64.3, and I'm just checking the endpoints to see whether or not those would be considered a minimum value. And in this case, they're not.